Got some past exam questions here on Year 12 polymers that you can use to test yourself with. So the link to the questions is in the description of the video. Click on the link, try the questions, and then watch the video for the answers. Okay, so question 1, got to add brackets to the section of the polymer for one of the repeat units. Well, there's 3 repeat units shown here, so I've just gone around the first one. Draw the structure of hydrocarbon B. So this polymer is made from hydrocarbon B. So all I've done is copied that repeat unit section out. See, there's the end bonds there, the dotted lines. So that part there is a double bond in the monomer. So all we do is we just put a double bond between those 2 carbons and we lose those dotted lines. So we get this structure here, and that's pent-2ene. Got a little calculation now. So we're told the polymer has a relative molecular mass of 50,000. How many monomer units are required to make 1 molecule of the polymer? So if we work out the MR of the monomer, C5H10, that's 70. So if the MR of the polymer is 50,000, so if we divide that by the MR of the monomer, we get 714.3. So you could either go for 714 or 715, but it has to be a whole number. Moving on to question 2, so we've got to draw the structure of the monomer that could be used to make this polymer. So it's very similar to the start of the previous question. So I've done the same thing again, I've extracted the repeat unit, so that's it there. I've just put some dotted lines to show the end bonds. And then all I do is put a double bond between the carbons and lose these. So we get that. Next part of the question is about the combustion of this polymer. So any polymer that contains chlorine is going to produce HCl when it's combusted. That's a toxic gas. That's one of the problems with chlorinated polymers. So suggest or describe a way in which HCl is removed. Basically boils down to the fact that HCl is acidic, and so you just treat it or react it with a base, or you could say an alkali or a carbonate. Essentially you just want to neutralize that HCl. And the final part of the question, an advantage of using polymers made from cornstarch over halogenated polymers, which are typically made from crude oil. They are renewable or biodegradable, you could say. Question 3 is a multiple choice question, basically the same as 2 that we've already had. So we've got this section of the polymer chain and we've got to identify the name of the monomer. So I've done exactly the same again. I've just pulled out the repeat unit, one of the repeat units, just put dotted lines on, and then that goes to a double bond. So what is this alkene? It's propene. So option D. Question 4, chloroethane. So I've put the displayed formula up there, can be polymerized to form polychloroethane. We've got to write an equation for that using displayed formula. So we just take the monomer, put a little n in front, which means a large number of, and then we just arrow, and then we're going to break open that double bond, put the n bonds through the brackets, and then just wrap it in a bracket, and then that little n goes on the bottom right hand side. Part B, we've got to come up with an equation for the incineration of the monomer, chloroethane, with oxygen, and we're told that it forms carbon dioxide, CO2 obviously, carbon monoxide, CO, hydrogen chloride, HCl, and one other non-toxic product. Well, that's going to be water because we've got hydrogen and oxygen knocking about, so the equation balances to that. And the last part of the question is virtually the same as question 2a. So explain how sodium hydrogen carbonate removes hydrogen chloride from the waste gases. It neutralizes the HCl, or you could say sodium hydrogen carbonate is a base. Question 5, we've now got to turn a monomer into a polymer chain showing 2 repeat units. So we need 4 carbons in the sort of backbone. Basically all you do is you just take the double bond, open it up, put the end bonds on, but we need to do that twice. Don't forget these end bonds must be there because that shows that this continues. And then part B, why does this manufacturer of polypropene nitrile have 100% atom economy? So you could say it's an addition reaction, or there's no waste product, or there's only one product. Part C, percentage yield calculation. So we're told that a factory is able to make 11.13 kilograms of propane nitrile, that's this stuff here, from 220 moles of propene what's that as a percentage yield? So moles of propane nitrile first, mass over MR, but remember mass needs to be in grams, so we multiply that by 1,000 to put it into grams. So that comes out at 210 moles, and then we know that the expected moles of propane nitrile is going to be 220 from that 1:1 ratio between propene and propane nitrile. So percentage yield, just actual moles over expected times 100, 95.5%. And finally, question 6, we've got to draw the structure of E-pentatoluene. So I'll just start with this diagram first. So that's just a sort of straightforward diagram of pentatoluene, and we're focusing on the carbons of the double bond. So on this left-hand carbon of the double bond, this methyl group's the priority group because there's a carbon directly bonded to the carbon versus that hydrogen. So this takes priority because the carbon has the higher atomic number. And then on this carbon, we've got a hydrogen and an ethyl group. Well, the ethyl group takes priority for the same reason. And so when we draw the E version, we sort of make it obvious that these are diagonally opposite. These priority groups are diagonally opposite each other. And finally, draw the structure of polypentatoluene, include 2 repeat units. So all I'm going to do is take my monomer, open up the double bond, put end bonds on, and draw that twice. And it gives me that. Don't worry about the relative positions of these two. I've kind of kept that going, but remember sigma bonds can rotate. So you could have your CH3 and your C2H5 next to each other because this can rotate around and put that ethyl up there.